I know a lot of us tend to be intimidated by learning any chemistry. It's not something we necessarily want to do. If you love chemistry, I'm very proud of you. There are not a lot of us out there who actively seek out chemistry classes. It's more one of those things that we seem to take because we have to. But I think that that's so unfortunate because when we learn some of those basic concepts of chemistry, it helps us to understand how atoms are interacting to make molecules, and molecules come together to make a cell. It gives us a deeper understanding of life. And like many of you, chemistry is not my favorite subject, but I see it as a tool that helps me to understand life and why living things do what they do, and can really help us to solve a lot of problems. So we look at an atom has three basic subatomic parts. We have our protons, our neutrons, and then surrounding that nucleus with our protons and neutrons will be our electrons. Electrons are constantly moving, which is why I like that second picture in the slideshow that shows this more three-dimensional shape surrounding the nucleus, and that's essentially communicating anywhere where our electron can be. But we need an abstraction. We need some way to be able to clearly and quickly communicate about the electrons so that we can get to the important part of an atom, the way how those electrons are going to behave and how the electrons are going to help determine whether or not our atom wants to bond. So here in our sample or our example atom that we have, hydrogen, we have just one little electron and we only have one electron shell. That one electron shell is going to be full if it has two electrons. But since we only have one little electron for our hydrogen, that means that this electron shell is unfilled. Hydrogen is going to want to make bonds. Anytime that outer electron shell is unfilled, that atom is going to want to make some bonds. And that's really the important reason why we are learning about atoms and their structure, is because we want to know whether or not they're going to want to make bonds. Because making bonds is what gets us to molecules, gets us to cells, gets us closer to life. Life is all about making bonds and all about breaking bonds. We have three main bonds that we're covering in our biology course: hydrogen, ionic, and covalent. I want to start with the hydrogen bond. When we have a hydrogen bond, all it takes is bringing one hydrogen atom close to another hydrogen atom. And remember, our hydrogen atom just has one lonesome old electron in its electron shell. So as soon as I get two hydrogens close to one another, of course they're going to want to form a bond, because when they form a bond, they're more likely to be able to complete that outer shell. Now, when we have two hydrogens bonded to one another, this is going to be a relatively weak bond. We're going to find some of those weak bonds in really important places, like in the DNA molecule, holding the strands together. We're going to find hydrogen bonds in proteins, helping to determine the folding and the structure of that protein. So even though hydrogen bonds are relatively weak, we are going to find them in some pretty important places as we move throughout the semester. Our next type of bond is an ionic bond. In the example from the lecture slides, we're looking at the example of salt. Now, salt is just two atoms that have come together, the sodium and the chlorine. When sodium and chlorine come together, the sodium is going to give up its electron, and the chlorine is going to take it in. By looking at those outer shells of both sodium and chlorine, it seems very logical and very reasonable as to why those two atoms are going to engage in that ionic bond, where one is giving and one is taking in an electron. Now, what I wanted to show to you is this little piece of Maldon salt. That's M-A-L-D-O-N salt. It's a special kind of salt, and what I love about it is when sodium and chlorine come together to make those ionic bonds, they'll start to form this little pyramid. If you're a salt lover like me, crunching into one of those pyramids is really, really amazing and wonderful. Most of the time we don't necessarily see salt that's quite that big and chunky. Now this salt will stay stable. Sodium and chlorine will be engaged in this ionic bond for a very long period of time. We'll talk a little bit more about what might break the bond between sodium and chlorine in just a few minutes. Our third type of bond is a covalent bond. With a covalent bond, we have a sharing of electrons between two or more atoms. Now, it's not always going to be an equal sharing of electrons. This is where we get to that classic example of water. Water is two hydrogens and an oxygen that have come together. And when those two hydrogens come together with the oxygen, they're going to form that covalent bond. Whenever we draw water, we tend to see it as this Mickey Mouse face, and the reason why it always ends up looking a bit like a Mickey Mouse head is because we want to show that unequal sharing of electrons. So remember, hydrogen just has one little old lonesome electron out here in its outer shell. And when these hydrogens engage in the covalent bond with the oxygen, those electrons are going to spend more time hanging out here at the oxygen nucleus than they will back home hanging out around their home nucleus. When we have more electrons spinning around the oxygen nucleus, that's going to make this side of our molecule more negative. Because our electrons are spending more time hanging out down here around the oxygen nucleus, it's going to make our hydrogen side more positive. So our water molecule is going to be polar. We have an unequal charge across the molecule, with the oxygen side being more negative and the hydrogen side being more positive. That term polar is a general generic term that we use in chemistry whenever we want to talk about the idea that our molecule has different charges in different places. Now, for those of you who have more of an engineering mind or more of a mind that latches on to geometry, this angle between our hydrogens and our oxygen and our water molecule will always be 105 degrees. So we have our three main types of bonds: hydrogen, ionic, and covalent. Now, I ended with the covalent bond on purpose because by looking at water as the quintessential example of this unequal sharing of electrons, this leads us directly into talking about the properties of water. Water is amazing. It's one of those molecules that's necessary for life, which is why when water was discovered on Mars, people got so excited because they said, wait a minute, we've got all of those other elements found in all living things: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We've got all of those up on Mars, and we've got water. So if we've got all of those things together, then it's gotta happen. There's gotta be life up there somewhere, right? I mean, all the bits are there. We've got life here. We've got all the bits. Surely there's got to be life up there. So that's why we've been going out and checking it out to see if there might be life. And one of the things that's amazing about water, and why I have this glass of ice water today, is because water has this ability to be solid, liquid, gaseous. That triple point is really amazing. We don't get into it much here in introductory biology, but in later classes, you may start focusing in on the triple point of water. Now, of course, when water is solid as ice, it has that ability to be able to float. It's less dense. We could talk all day about climate and about how the ability for ice to float allows our poles to exist and allows that to govern our climate cycles across our planet. But again, now we're starting to stray into environmental science. So a couple of properties of water are important. One property of water that we focus on a lot here in introductory biology is that ability for water to break the bonds of other molecules. So remember that big chunk of salt, that nice little pyramid. Sodium and chlorine have been in that stable ionic bond, but as soon as I bring in the third wheel, as soon as I bring in water, water has the ability to tear sodium and chlorine apart. Part of the reason for that is because of the polarity of water. So when sodium and chlorine engaged in that ionic bond, sodium gave up its electron and became more positive. Chlorine took in that electron and became more negative. They became ions. So water comes in, and because of its polarity, and because sodium and chlorine have become ions, water can just rip and tear that very stable bond apart. So the positive part of hydrogen is going to grab onto chlorine and say, "Chlorine, oh, you've been with sodium for so long. Why don't you come with me? I will show you a good time." The negative part of oxygen will grab a hold of sodium. "Hey, sodium, oh, you've been with chlorine for so long. You've been in that relationship. Why don't you come with me? I will show you a good time." So the polarity of water is able to rip and tear the sodium and chlorine apart. Water is incredibly good at breaking the bonds of things. This is why water can do erosion, that ability to move across the landscape and break the bonds of the atoms that make up rocks and make up really sturdy things. I mean, if you want to know how good water is at breaking bonds and breaking things down, just own a house. Within a few years, you're looking for all the places that water is getting in and trying to keep it out, because everywhere it gets in, it just destroys the bonds, and those bonds start to crumble away, and next thing you know, you're having to replace houses or windows and doors, and the whole thing is just falling apart. Water, it's amazing in its ability to be able to be a solvent, to break things apart. So there are other properties of water that are talked about in the textbook, but I think for now, in introductory biology, it's really important to focus on that ability of water to break the bonds of other substances. We are going to classify different things based on how they're going to behave in response to water. Something that is attracted to water is called hydrophilic. Something that is repelled by water, like my cats, are called hydrophobic. The next thing that we need to talk about, as far as basic chemistry is concerned, is talking about classifying substances based on how they respond when we drop them into water. So, this is where we get into the topic of acids, bases, and neutral substances. Essentially, when we're talking about these, or using these terms, what we are doing is we are classifying substances based on how they're going to respond in water. We are measuring that ratio of hydrogen to hydroxide groups. So water has that ability to break apart. We're going to measure that with pH, which is potential hydrogen, and essentially we're measuring that ratio of hydrogen ions to hydroxide. If something has lots of hydrogen ions, or has more hydrogen ions when compared to those hydroxide groups, we're going to call it an acid. If something has less hydrogen, but more of those hydroxide groups, we're going to call it a base. Now, as a term that we use in biology, we use the term neutral. And a lot of times we have this, we just get hung up on the term neutral. We tend to overemphasize it, or we tend to focus on it too much. There's this misconception that neutral is like, it is the ultimate thing. Everything is striving to be neutral. And that's not true. Most biological systems are manipulating or sensing and responding to either being more acidic or shifting more towards a base, shifting the ratio back and forth. Systems are not trying to be at neutral. And when we use this term neutral, the strictest definition is that it's an equal ratio of hydrogen to hydroxide groups. And really, the only time we're going to get that is pure water. But sometimes what will happen is you'll have some distilled water, which is just pure water, nothing else in it, just H2O. And you go to measure it with some pH tape. And the weirdest thing happens, it shows up a little bit more acidic. And the reason why that is happening is because you happen to catch the water at just the moment when there were more hydrogen ions that had split away from the water molecule. And so you're picking up on that, you're measuring that, which is why your pH tape is showing up a little bit more acidic. So when it comes to biology, when it comes to biological systems, don't get hung up on the term neutral. We're rarely going to see that in biological systems. What biological systems are going to be doing is responding to acids and bases that shift in the hydrogen to hydroxide ratio. So I want to show you just a couple of common acids that you probably have around your house. This is vinegar. Vinegar is typically 5% acetic acid. There's 95% water in this solution. When I drop this into my glass, what's going to happen is my acetic acid is going to split apart, and I'm going to have more hydrogen ions in my solution. Lemons, they produce a lot of acid. They produce a lot of hydrogen ions. When I add this lemon juice to my water, it's going to make it taste delicious. But what I've done is I've shifted the ratio of hydrogen ions. I now have a lot more hydrogen ions. And when I taste it, part of what I'm going to be tasting, that kind of bite, is going to be those hydrogen ions. The hydrogen ions have the ability to do a lot of damage. I could take this lemon juice and I could clean my toilet. The reason why I can use lemon juice to clean my toilet, or vinegar, is because there are so many hydrogen ions. They're going to destroy the bacteria. They're going to disrupt that lipid bilayer that defines the cell. So acids are great at destroying systems. Maybe inside of your stomach, you've got that bubbly tummy. Your stomach has been releasing a lot of hydrochloric acid that's been breaking apart into hydrogen ions. And part of the reason why you start to feel upset and is because of all of those hydrogen ions. So you go running for something like an antacid. This is a buffer. Buffers are either going to work on acids or bases. This bicarbonate buffer is going to, once I eat it, go down into my stomach and immediately start grabbing all of those hydrogen ions. This antacid works on acids. And the reason why I start to feel better is because it grabs all those hydrogen ions. It locks them up. It shifts that ratio of hydrogen to hydroxide ions by grabbing them and grabbing them out of the contents of my stomach. And that's why I start to feel better. If I had a base and I used a buffer, the buffer is going to work on that base by either releasing hydrogen or grabbing all of the hydroxide groups. Again, shifting the ratio. So when we're looking at pH, when we're classifying substances as acids, bases, or neutrals, one of the things we're looking for is shifts back and forth in that ratio of hydrogen to hydroxide ions. To give you a little example, inside of your body, if you start to move around, if you start to exercise, the first thing that's going to happen is each individual cell is going to start to release more carbon dioxide. When that carbon dioxide gets into your blood, it's going to interact with the water and make something called carbonic acid. That carbonic acid is going to get measured, that shift in your blood pH is going to get measured by your hypothalamus. When your hypothalamus measures that shift in the hydrogen ions in the blood, it's going to send a signal to your heart and send a signal to your lungs. That signal is going to say, breathe more for your lungs, beat more for your heart. We need more oxygen. We need to shift that ratio back. We need to eliminate some of those hydrogen ions. So our increase in heart rate and breathing is a direct response to that change in pH in our blood, a change in that ratio. Well, hopefully this helps you to understand sort of the basics of chemistry. Why we have to get down to the level of atoms. It's all about the electron shell and the electrons, whether or not our atom is going to want to bond. So a filled shell means it's not going to want to bond. Unfilled shell, outer shell, means it does want to bond. There are three types of bonds, or hydrogen, ionic and covalent. Hydrogen the weakest, ionic where we have a giving and a taking of an electron. Covalent where we have a sharing of electrons. Bonding is all that life does, breaking and making bonds. And then we look at water, that quintessential example of a covalent bond. Water is essential for life. We classify substances based on how they respond to water. Hydrophilic, loving it. Hydrophobic, hating it. And then we also look at how substances are going to respond to water as far as that hydrogen to hydroxide ratio, measuring those hydrogen ions and hydroxide ions to classify something as an acid, base, or neutral. and then looking at which substances could be buffers that could help shift those ratios of hydrogen to hydroxide ions. If you have any questions, please make sure to email me. I want to make sure that you understand these basic concepts of chemistry before we get into the more complicated stuff of the cell.